Hello everyone, so today I'll be showing you the most basic, the most fundamental principle of calculus, the most useful component, and that is the limit, as I showed you in the last video. That's just the value a function approaches when it seems to not really change too much, or when it seems to change much, but indefinitely. So normally we measure it as the input value, the x approaches infinity or 0. I've never seen it approaching minus infinity, but I think it's possible. I think the key idea here is that the value you're trying to look at is approaching some sort of abstract concept, which 0 is. It's a number, but it's not, you can't divide by 0, so that's why often you end up having 0 in the value that x approaches, because often it would be useful to see where a function is going, rather than just calculating the function with x equal to 0, because that's just not going to work. So that's why limits are very important. And now I'm just going to show you, instead of just giving you a really prolonged kind of introduction. So limits, that's the topic of today. I'm going to bring it closer. This is the notation for a limit. This is just a random function I thought of. Okay, so what does this mean? You can break it down into little steps. Lim, needless to say, that just limit. And the arrow means approaches or tends towards. Either way is fine. And the value we're expecting here is going to be as follows. What you need to do essentially is just gradually kind of compare the values. So you see 1 over 1, we start with 1. 1 over 1, with n being equal to 1, is just 1. And then 1 over 2 is half. So yeah, you see that, what can you notice here? It starts off as being 1, then it becomes half, a third. What about a random value? Let's just do 456, and we get this, and that's, I don't know if you can see, but it is very close to 0. Well, not very close. If you do 1 over 99999, that will be closer. But the point is, this shows that as you increase n, the value for this function is going to be closer and closer to 0. It's never actually going to be there, because you can't divide 1 by infinity, because that infinity is not a number, it's a concept. So that's what limits are for. Limits are for expressing 1 over a concept, 1 by a number that's either very, very big or very, very small. So this is why we need limits. It always comes from this mathematical notion that you can't divide by infinity and you can't divide by 0. So we just kind of simplify things for us. And in calculus, they're very useful. So I'm just going to show you another example. So limit. We limit as x approaches infinity of it's not n. X squared minus 5, and yeah, let's just say x squared plus 9998. Doesn't matter. Okay. How do you approach this? And by the way, I'm just gonna clarify for you. What you're trying to avoid is you're trying to avoid writing this, because this is an indeterminate form, which means it doesn't really have a value on itself. It just shows you that there's a different way to express it, so I'm not going to delve into that, but what I'm trying to show you is that in a limit we're trying to avoid using that kind of notation, which is wrong, speaking from a very strict mathematical point of view. But then again, it's fine if you're working out a limit and you want to make things easier for you, then you can write it that way, and it's fine as long as you appreciate that that's not the correct way of doing it, and that it's just like a temporary thing. Okay. So often the way we do it is we just divide how much we need to just show that certain values here are going to become irrelevant in terms of comparison with x squared as x approaches infinity. So what we're doing here is essentially we're just taking over terms here and showing very explicitly which values here will matter and which other values will not matter according to that order of magnitude. So then here we have 1 minus this, okay, 1 plus. Now, this is where a very peculiar question is kind of summoned, and that question is, how do you define infinity? Because surely you can have different types of infinity. You can have a really big infinity, and you can have a really small infinity. If I add up, if I find the number of insects that live in this world, that will be a very, very large number, but it won't really be infinity. But then, if I count all the star systems we have in the observable universe, then is that number, considering that we can think about it as infinity, is that going to be the same as the amount of stars we have? Of planets we have, because you have many more planets in a given solar system than we have stars. So then you can kind of think of things that same way. So if we have x squared and x tends towards infinity, that infinity is going to be bigger than x on its own, with x being infinity as a limiting value. So what we do here is we just kind of think, just like I mentioned before, x squared is going to be a much bigger value than 5. It will be a much bigger value than x, but we're just talking about comparing it with a constant here. 5 doesn't really matter. It can be, again here, it doesn't matter if it's 5 or even 5 million. It doesn't matter. Compared to x, which approaches infinity, it will virtually be the same thing as 1 or 0, or it could be anything. So what we often do with this is, if we see there's any fraction with a term of the value that approaches infinity as a denominator, then we just cross it out. So then what we're left off with is 1 over 1. So that's our answer. I'm not going to go into the derivative definition with limit, but I'll definitely do it next video. So I hope you found this useful, and we'll discuss things in the next lesson, as I mentioned before. Bye.